What I want to do is a little bit more today with the work equals the conservation of dynamical energy concept, work another problem or two out with you. I don't think they're up and running yet.
No, they're recording, the monitors just aren't on.
The monitors just aren't on? Okay, thanks. And then secondly, I want to maybe work another problem or so with you on linear impulse momentum, which we sort of wrapped up during the last session as far as the concept goes. And then we'd like to start on an introduction to angular impulse and momentum. All right. So what we'll do today is to start out is I picked a problem out of the book. It's got a little bit of friction in it. So come on over here and take a look at this. Here we have a three-dimensional configuration. And we have an object that is up here at location A on this rod, and it happens to have a velocity of 6 feet per second down that rod. When it arrives down here at B, it's going a little bit faster. It's at 10 feet per second. There's a spring attached out here. Happens to have a stiffness of 2 pounds per foot and an unstretched length of 2 feet. So what's going to happen is there is some friction on this rod. And the question is asking for the loss in energy due to friction. Let's see, when it asks for the loss of energy due to friction, what would we be calculating?
Energy at the beginning of the system, the energy at the end of the system. And then
okay, so it would be the work done, right?
By the friction.
There would be the work done by that friction force. Now, if you think about it, you have the weight of the object, which would be vertically downward in the negative z direction. So you have the weight of this mass, this collar, 5-pound collar. And then you also have the changing direction of the spring force. It's going to vary in its direction. That spring force is going to vary in its direction between my finger and the pencil point as the object moves down along here. The spring force is going to vary in its direction and in its magnitude. So it's not simple to calculate what that variation is. So that's why they're saying, first of all, just compute the work done or the energy loss due to that friction. Then they want us to figure out what the average friction force would be during that motion. The average friction force would be. Okay. So we have a XYZ axis system as shown. And the dimension out on X is what, 3 or 4?
3.
3 out here?
Yep.
Okay. So that's 3 feet. And then I think it's 4 feet vertically?
Yes.
Okay. And then we have the rod then goes out to, what?
3.
3 out here? Okay, good. And so our rod comes down along here, and then the spring is attached to this collar. And the object was moving from this location, initially had a speed of 6 feet per second, and ends up down here traveling at 10 feet per second. And there is a friction force here acting that's variable. That friction force is variable. And it acts throughout that distance. And you know that since we have an orthogonal axis system here, we have an orthogonal axis system, and then this is a 3, 4, 5 right triangle. So that friction force, the work done by the friction force is going to act, the friction force average, or let's do the work due to friction, is going to be equal to, it's opposing the direction of the motion, so it's negative. And there's going to be, what they were asking us for, one part of the question was what that average friction force was acting over the distance of travel. So this would be this value that we get here for this work is going to be the energy loss due to friction. This would be the energy loss due to friction. Okay. The stiffness was 2 pounds per foot, I believe. Is that correct?
Yes.
Okay. And the unstretched length of the spring was 2 feet. Okay. So these pieces of information are all provided. So the spring is initially at this location, and they labeled that, what, B?
They call that A.
Oh, this is A up here initially.
B's down there, right there.
B's down here. Good. Okay. So what we can do now is start writing the equation. And you folks could take a stab at it if you want to just try doing it without looking at my equation writing. So we start always with the governing equation, and I'd really recommend that you do that. And we have, one thing I forgot on my picture was mg. This thing weighed how much? 5 pounds. So there's our weight. 5 pounds, always straight down. So we have gravity acting, we have the spring effects acting, the spring force acting, which is going to be, I believe, in tension always, because this spring is always going to be longer than 2 feet. So it's always going to be in tension. So what I could do, just to make my free body look a little nicer, is I could actually label the spring force in there F sub S, acting on the body. Okay, so the only forces that are active, the only active forces other than gravity and the spring effects is due to this friction. So that's what's embodied in this work here, is just that. So we're going to have the work done due to friction is going to be equal to the change in the dynamical energy over here, the change in the dynamical energy. So we're going to have 1/2 our mass, which is 5 pounds divided by 32.2, so that's going to be units of slugs, which is about the only time I've mentioned that word this term. Slug units on the mass. And then we're going to have our speed at B, which is going to be 10 squared, and we're going to be subtracting from that the speed that it had initially, which was 6 squared. And notice that this is 10 squared minus 6 squared. It's not 10 minus 6, the quantity squared, which I've seen in an error in a kinetics problem or two that a couple people have done. Change in our gravitational potential. Change in gravitational potential is going to arise from the change in distance off of a datum. Why don't we let the XY plane be our datum? So down here at the lower level. So then the change in gravitational potential is the weight of the object times its position at the end of the motion relative to the datum, which is here at B, so it's down on the datum. So there's a 0 position, and we're subtract from that the elevation off the datum initially, which happened to have been 4 feet. Plus the change in the elastic potential. You remember what that is as an expression?
1/2 K change in spring length.
1/2 K, and K is 2 pounds per foot, times the change final minus the change initial. So the final position is down here at B. Down here at B. Notice that this base is a 3, 3, and so there's a diagonal essentially of a square down here. And you should be comfortable with knowing that that's just on automatic, that it's that length is 3 radical 2. So that length of spring at this point is 3 radical 2, but remember, we don't use that value, we use the difference between that length of the spring and its unstretched length. So it's going to be 3 radical 2 minus the 2, and that quantity is the distortion in the spring. In other words, that's the delta that exists in the spring at location B, and then we have to square that. We subtract from that. Is it a difference or a square, or is it a sum? Is it a sum or a difference now?
Should be a subtraction.
Hmm?
Should be a difference.
It's a difference, isn't it? Okay. And so we need it up there originally. Oh, at this location up here, it is, the spring is a big long 5 feet. Again, a 3, 4, 5. So that length is 5 feet minus the 2 feet. So it's 5 feet minus 2 feet, and that distortion at A has to be squared. So it's 1/2 K delta final squared minus delta initial squared. Everything on the right side here is numeric, so we can pop that value out, and that's going to be then the energy loss due to friction. If somebody would punch that up, that might be handy. Typically, I don't start punching right here. I usually do a little bit of cleaning up, so I can see 2 into 5 is 2.5 over my 32.2. And I've got 100 minus 36 is 64. And then here I have negative 20. Down here, the 2's disappear. And we're left with that difference squared minus 9. And that's going to be equal to this U due to friction. What's this 3 rad 2 minus 2?
4 minus
22 minus 6 root 2.
No, I just want that value.
That would be 2.24
After you squared or before?
after 5.03.
Before?
After squaring.
Oh, after squaring, yes. So you said what, 5 point?
5.029, so 5.03.
29? 5.3, okay.
5.0, sorry.
Oh, sorry.
About 5.03.
Thank you, good. Okay, now what I want you to notice, folks, is always pause on this thing. It looks like there's an increase in kinetic energy. You can see the positive value here. it looks like there is a loss in gravitational potential. And go back and look at the picture. That should make sense to you. There's a loss in gravitational potential. It's given up. It's come down from up here down to this lower level. And then look here, it looks like the spring has lost. It looks like the spring has given up some potential. Does that feel right?
It's become less.
Yeah, 'cause the spring is.
The spring was 5 feet long, minus the 2 original, so it had 3 feet of stored energy in it. It had 3 feet of distortion energy in it, okay? And then down here, it's much shorter. So it should have, you can see it, if you look at the physical situation, those values, the sense that you get from that should show up in your equation. Instead of just blindly relying on what you're punching out there. Okay, so anyway, you should get a final value there, which is what? Everybody got it?
About negative 21.788, so negative 21.79.
7.9, and the units on that would be
The energy, so we need pound feet.
pound feet of energy. And then that
That's
value.
something different. I got negative 19
I
even.
did too.
Okay, majority rules.
Let me recalculate.
Repunch. Okay, negative 19 point what?
0.001, so pretty much
Okay.
negative 19.
Negative 19.
Yeah, about negative 9.
Okay, and then that's going to be equal to, come back up here, that's going to be equal to minus F times 5. Minus the friction, the average friction force, times the travel distance 5. So you take that, and so F then, average, is going to be about very close to 4, just a touch under 4, if this 19 is correct.
Negative 3.8.
Excuse me?
Negative 3.8000.
That negative
3.8 pounds.
all that
In the direction that I've shown here, because I originally,
Right, yeah, in that direction, so it's positive now.
in that direction, so because the work is negative there.
Okay, I agree.
Okay, good.
And that negative we were carrying around just signifies that that's going not along our path, the force.
Yeah, it's going in the opposite.
Opposing the direction of the motion. Opposing the direction of the motion, yeah. Negative work being done. Yep. And that's why we ended up with a positive result then, is because we were very careful to assign a negative to that product there.
Right.
Okay? So it's a pretty basic problem, but nevertheless it's useful to run through things like that. Okay. Any questions on that? 168, I think was that question.
Question on the setup of work energy problems.
Excuse me?
Question on the setup of work energy problems.
Mm-hmm.
Do you recommend and how and what are some pros and cons to setting up the method up with the initial energy and the final energy and the difference between those being work done instead of setting up each of those difference
Yeah.
internally on the right side? Same thing,
In this
just
course,
setup.
now in physics, you've probably done them by taking the energy in the system initially, energy in the system after. But then the question might arise if you get away from that stuff for a while, where do you put that work that's done by everything else? So you just have to be careful about it. You know, I can understand your work. Anybody that teaches this stuff, or you folks can understand each other's work when you lay it out neatly. But I just for consistency, a lot of people at this level, just having a nice, clean, consistent way of doing this, it makes it just, you can see the parts real easily. You can also see them the way you're describing. So you can do them either way, just lay it out nice and neatly and be real clear about what you're doing. Okay?
Okay.
So I don't mind, as long as you get them right. Okay? I was thinking of doing another one here. Actually, this one might be kind of fun to take a couple minutes on. Let me see if I can come in a little more on that. This is over on page 192. So we have two masses. One mass is twice the other mass, and they're connected by a rod, a massless rod. And slides with negligible friction and a circular path of radius r inside this vertical circular ring. If the unit's released from rest when theta, defined here in this picture, is 0 degrees, in other words, the 2m value is sitting right up over here where my finger is, and then this thing's in and then the other one would be down here at the bottom, and then they're going to slide around and oscillate. Determine the velocity when the rod passes the horizontal position, so when both masses are horizontal from each other, and then figure out the maximum velocity, and then figure out the maximum value of theta. How far will it swing? Okay. So theta is defined off the horizontal for the double mass. Rigid rod connecting them, and that defines angle theta. So if we call the datum right here, write our equation based on that, this is some radius r, then the three pieces we were looking for were the velocity when they're horizontal, we were looking for the maximum velocity, and we're also looking for theta max. Okay. No friction. Right here is the starting spot. Theta equals 0. We're at rest, and then we let it go. So geometrically then, the masses are going to be sitting here like this at rest. Okay, then this is going to be its initial position. Let it go. Here's its general configuration. All right? So, there are normal forces acting. N sub m, N sub 2m. But those normal forces will do no work. Right? But we do have 2mg as a weight here, and over here we have mg acting. No springs. So our governing equation then, U equals delta T plus delta Vg plus delta VE. We can zero out the elastic potential change. We can zero out the work done by, since there are no other active forces other than gravity. And then we just have this balancing act existing between the change in kinetic energy and the change in gravitational potential as a function of theta. So 0 is equal to, remember, when you have multiple masses, each mass is carrying kinetic energy if they're in motion. So be sure you don't forget one of them. So we have the 2m mass at some velocity. Now,
At the same velocity. They're connected by a stick.
yeah. Okay. So they are in circular motion, aren't they? Both masses are in circular motion, and you know that on a circular path, just draw part of it like this. On a circular path, the speed it's carrying, this is our 2 mass, double mass velocity, that's going to be equal to r theta dot. There's theta, so that's going to be equal to r theta dot. This other mass, similarly then, is over here, and it's carrying r theta dot speed also, isn't it? So as you mentioned, they're both carrying the same speed. Okay. So our double mass particle then has some speed, v sub, let me just call it v squared, minus the initial squared. The other mass, don't forget to include it, is just made up of the mass of m, again carrying speed v, being squared, minus 0 squared. Plus, each mass is changing its potential. Each mass is changing its potential. Here's the initial position, and I set a datum up here. We set a datum up at this level. So as this thing moves down, it gives up this double mass right here gives up some potential as it's coming down, and the other mass is actually is going to actually be rising up or gaining some potential in the motion. Okay. One thing I didn't mention is these are both then at 90 degrees to each other because of the defined configuration. The two masses were at 90 degrees to each other off the central angle there. Okay, so if we take our twice mass times g, then we need to look at its change in gravitational potential. So it has given up its final position in the general configuration here is below where it started, and that distance happens to be careful, r sine of theta, and it's negative. So it's negative r sine of theta minus its initial value was up here at the datum. Then we have the other mass, m, its weight mg, and its final position, you want to be careful here.
Its initial position or its final position?
Yeah, its final position is down. Here's the way I usually do these. It's r below, and then we come back up. Well, actually, I guess I could just look here, but this is pretty nicely defined, isn't it? R cosine theta below the datum. Okay, r cosine, it's the adjacent edge right here. This length is right there, if you can see that. That value is r cosine theta, and it's below the datum level, so it's negative. It's going to be minus r cosine theta, and it initially was at negative r. So be careful. What do you do here?
Minus negative r.
Minus a negative r. Watch out for that. And we have that equal to 0. So it looks like every term involves m, so I think we can get rid of that. And let's see if we can tidy that up, and I'm going to erase some over here. Move over onto this other board. So what do we have? Oh, and we could lose, I guess, this pair of 2's. And then we have v squared plus a half of v squared. So that looks like 3 halves v squared.